Now, I want to warn you that everything I tell you is more or less true, but there are all kinds of complications, things like the memory model, which I'm not going to talk about because I don't have time and because it would be a bit of a distraction. So what I tell you, the high order bits are true, and the low order bits are either complicated or research questions, or maybe not as true as it appears. So be aware that there are there are some things that are more complicated than I'm going to tell you. Things like if you want to do conditional weight, I'll tell you how to do that, but it's not as simple as everything else. False conflicts, you might have two activities that don't really conflict, but if you program it in the wrong way, then it will appear as if there is a conflict to the runtime system, and that will slow you down. The lecture this afternoon will talk about ways of transforming transactional programs into programs that have fewer synchronization issues. Resource limits are a big deal. If you run out of buffer space and things like that, then these are things that are very real problems that are difficult to talk about at a high level of abstraction. But it's better to have these problems than the problems that we had before. So every new invention replaces old problems with new problems, and if it's a good invention, then the new problems it's easier to live with the new problems than with the old problems. Let me check, how am I doing on time? 15? 35 more minutes, okay. Yeah. Okay, so composition. Remember we had this problem where I wanted to move something atomically from one queue to another. And I was faced with this problem that it's impossible if I use internal synchronization, but it's dangerous to provide external synchronization because it's too powerful and too unstructured and too hard to use. So I can do this very easily with my atomic construct. So on this line, I dequeue the item. On this line, I enqueue it. And I put the entire thing in an atomic block. And so what I'm saying here is that I don't care how Q1 and Q2 do internal synchronization. I want these two steps to be atomic. I'm not exporting locks that the client needs to remember to lock and unlock, where the client needs to worry about deadlock, all of these complicated things. I simply say, I want these things done atomically. And as long as I can do this efficiently and correctly, then I've solved this composition problem. And again, this is a very simple problem that would be very hard to solve in conventional programming, but here we have the simple problem is simple to solve. And what I like about this is the fact that simple problems often have simple solutions in a transactional model, which is not true in conventional models. Conditional weighting is a little bit trickier, but it can be done. Here on this construct and the next construct, I'm going to be describing constructs that were implemented in the Haskell programming language. I'm not going to write them in Haskell because I don't know whether anyone can read Haskell, so I'm writing them in Java-like script. But these are things that actually exist in programming languages. Here, for example, I want to do conditional weighting. I want to remove something from dequeue something from a double-ended queue, and I come in, I find the queue is empty. And so what do I do then? Well, instead of, in a monitor, you would release the lock and go to sleep and leave a note to the operating system saying, wake me up sometime. Here, what I'm going to do is I'm going to take my transaction and I'm going to say, roll it back to the beginning of the transaction, undo everything I did, and wait for something to change. And when that changes, wake me up and I'm going to start over again. So here we are exploiting the speculative nature of transactions. I'm saying I got this far, I don't like what I saw, pretend I never saw it. Just go back, undo everything, go to the beginning, put me to sleep, and if anything changes, wake me up and let me try again. Now, of course, if you wake up, there's no guarantee that you'll find something, but this is true in monitors and in conventional systems as well. So roll back your transaction and restart when something changes. So this turns out to be a very powerful way of doing conditional waiting. Implementing this, of course, represents a number of interesting challenges, but it's not really much harder than implementing other conditional waits. Yeah. Oh, that's a, so here you go back to the latest atomic of lock. Oh, the scope of changes. So, currently, no. So what happens now is that what the runtime system does is if you roll back, it remembers everything you read. And if anybody changes something you read, yes. So you go along, you read things, then you say, nope, I don't like this. You go back, and the runtime system says, I remember, that transaction read this stuff. As soon as something changes, it says, okay, so now it will see something different. There's no reason to restart if it sees the same thing. Now, of course, there's no guarantee that because you see something different that you see something you like. And so it's possible you wake up, nothing that, I don't like this, go back. But this is hard to avoid. So doing more sophisticated techniques, like you could say, roll back, wake me up when this predicate is true. But that also has all kinds of problems. What if the predicate has side effects? This is really a language design question. And language design in this area is not very advanced. Something that's unique in this area is, remember I said that composable waiting was difficult. I want to wait for one thing, or I want to wait for something else. And this is very awkward to do in most modern programming languages, but it's simple to do in something like in a programming language that supports transactions. In fact, the Haskell STM system solves this. So I run one method, so I do a DQ. The DQ can't find anything, so it says retry, wake me up later. Instead of going to sleep, I say, well, I have an or else clause here, so I'm going to try the second method. So or else says, try this. If it doesn't work, then try something else. If neither one works, then you retry the entire statement. So it's a kind of hierarchical awaiting property. And this gives you the ability to say, well, wait, let me know when something changes in one buffer or the other buffer. So this is a modular solution to this problem that has no real solution in Java or related languages. So these are the kind of high-level concepts that we want to implement. So at this point, what I hope is that you saw these constructs and said, yes, I see how an idealized form of transactions can solve all of the problems that we have with conventional lock-based synchronization. So I see in principle, this would indeed change everything. And all of these programs, all of these software engineering issues that are currently so difficult would be much simpler. Now, of course, it isn't true that everything that was hard before has now become easy, because as we'll see, there are many imperfections and many places where abstractions don't quite fit together. but nevertheless, the net result is still, should still be better. So I'm going to start at the very bottom and talk about hardware support for transactions. Now, historically, this was the first work that was done in this area. The intent was to make it easier to design lock-free data structures. So one of the things that makes lock-free data structures so hard is that we basically have only one tool, which is a compare and swap, or its relatives like load, link, store, conditional, which work on only one word of memory at a time. So compare and swap says that, look at this word of memory. If I like what I see, then replace it. If I don't like what I discover there, then leave it alone and tell me what happened. And do this all atomically in hardware. Now, the problem with changing only one word of memory is that often, if I want to do something like link something into a list, I want to change 2 words of memory. And you can do this with compare and swap by introducing levels of indirection, but that's slow and complicated and ugly. So wouldn't it be nice if we could change 2 words of memory simultaneously, have a 2-word compare and swap? But why 2? Why not be able to make atomic changes to multiple words in memory? And then we thought, well, this sounds like something, oh yeah, this is the notion of an atomic transaction from the database world, except having to do with a multi-core memory. So let me tell you how to do this. So first thing to say is that you can now buy processors that support transactions in hardware from Intel or from IBM. And there's, at this point, several generations of these things. Again, in order to use them effectively, you pretty much have to understand how the machinery works. In the future, perhaps, when we understand these things better, we can hide some of the details. But for now, you really need to understand how things work underneath so you understand how things can go wrong. Now, the basic idea is that multi-cores, at least most of them, have something called cache coherence. And I'll explain what that means. This is a way of making your memory appear to be faster. And what we're going to do is we're going to take conventional cache coherence and change it a little bit to give us atomic transactions. Cache coherence already uses hardware to detect synchronization conflicts. If I write something and you read it, the cache coherence mechanism will detect that. And this is exactly what we need for speculative transactions. And in particular, if I have a copy of some data that I've read, and you go out and write it, then the cache coherence mechanism will detect that I read something that is no longer valid, and it will tell me, hey, you better throw that information away because it's no longer any good. And this is also something that does almost everything we need for atomic transactions. So here's how standard cache coherence works. I'm sure many of you are already familiar with this, but I'm going to cover this anyway just so that it's fresh in your minds. So here we have, at the bottom we have memory. Now memory is really far away. Tens of cycles is now maybe 100 cycles. So memory is sitting on the other side of the river. And anytime I want to read something from memory, I write down an address and give it to somebody on a bicycle who rides across the bridge, gets that information, and then rides back again. So you really don't want to communicate with memory any more than you have to. And every year, memory gets further away. Not because the memory gets slower, but because the processors get slightly faster, the interconnect gets more complicated. And the bigger memory is, the more complicated the machinery needed to maintain it. And so the memory access time goes up rather than down. Between the memory and the processors, there is a communication medium. So here I've marked it as a bus, but it could be a full network. It could be running TCP/IP. I'm going to present this example as if it were a bus, which you can think of as a small Ethernet for simplicity, but it could really be any communication medium. And the idea is that each processor can broadcast a message on the bus, and everyone, including the memory, will receive that. At the next layer, we have caches. Now, a cache is like your desk. So I can read or write something from my cache in 1 or 2 instruction cycles. So it would take me 100 cycles to read from memory, but maybe 2 cycles to read from my cache. So if I ever need to read from memory, then I've got enough time to do lots of other things. But if I want something right away, then if it's in my cache, then I'm happy. So here's what happens. So a processor decides it wants to read the blue piece of data from memory. So it broadcasts a message on the bus saying, I want to read from this address. I want to load item X. And then the memory, who's listening to the bus, the memory controller says, oh, I have that. And then it broadcasts the data on the bus and loads it into the processor's cache. And the processor marks that data. This E here says is exclusive. It says, I know I have the only copy of this data. And I can do anything I want with it. But because I have the only copy of the database of this data in the world, and so there's no problem with concurrent access. Okay, now the next processor wakes up, next core, and it wants to read the same thing. So it broadcasts a message saying, can I please read X? Then its neighbor, who can respond quickly, says, oh, you want X? I have a copy of X. Please share mine. And so the neighbor responds by broadcasting the data on the bus, and it changes the tag from exclusive to shared. So that processor says, okay, I now know that someone else has a copy of this, so I need to be a little bit careful because I have a copy when someone else has a copy. So I have to, if I want to change this, I need to be sure that I don't cause confusion. Okay, now the red processor says, I want to write to X. I want to store a new value there. So it's going to change the data. And what it does is it first sends a message saying that if anybody else has a copy of this, throw it out, because I'm going to change it. And this is called invalidation. So the processor that had a copy gets a message, says, oh, I'm going to mark this data as being invalid because it's no longer the truth about the state of this data. And one way to do this is to say that the cache acquires a right to permission. So now at this point, the data sitting in the middle processor's cache is not the same as the data in memory. It's been modified. It's expensive to write it back, so we're going to be lazy about writing it back. Nobody else can have a copy of this data because it's been modified. Once one cache acquires write permission, the others lose their read permission. So this is all fairly standard. Because the memory is so far away, it only responds if it's not present in any cache. And when we change the data in our cache, we don't write it back to memory until we have to, because it's slow and expensive to do that. So now what I'm going to do is I'm going to take this standard picture, which I just gave you, from for your first year architecture class, and I'm going to tell you what you need to do to make this support atomic transactions. And this is basically what the Intel and IBM architectures do. Of course, what they do is much more complicated because they have to deal with more complicated situations, but the basic design is the same one. So we have the same situation where we have memory interconnect caches. One processor says, I'd like to start a transaction. So it executes the atomic statement in the code that I showed you. And it says, I want to read this on behalf of a transaction. And now it marked the cache line as being transactional. So we need an extra bit in each cache line. So now the second processor does the same thing. It says, I'm going to start a transaction and I would like to read that location on behalf of this transaction. So at this point, we have the same data item cached in two caches, both of them marked as being transactional, which is to say they're speculative. Okay, now one processor wants to commit its transaction, meaning it says, okay, I want to finish the transaction. And what it does then is it just says, well, everything is okay. I'm going to take that transactional bit, I'm going to clear it and set it to valid, meaning that this is just regular data. And then now the second processor says, now I want to write that transaction. I want to write that data. So it, just as before, it updates the cache copy. And now it marks it as transactional and as dirty. Dirty means that it disagrees with the copy in memory. And so if that transaction commits, you're going to have to write to memory. While the transaction is going on, you cannot write this to memory because it's speculative data. It isn't real yet. And so we don't write tentative data to memory because we have no way of recovering it. So this is one difference from conventional cache coherence. In conventional cache coherence, you can always write dirty data to memory. But in transactions, you can't. You have to keep that in the memory. Okay, so let's rewind and let's go back to the previous state and replay this in a different order and see what happens. So I'm going to introduce a synchronization conflict, and we can see what happens. So now both transactions are active, both have read the same data, and both have that data marked as being transactional. So now the green processor says, I want to write this data, and it broadcasts an invalidation message. The red processor says, oops, this data is transactional. I read something transactional that has been invalidated. I must cancel, abort, roll back my entire transaction now because there's a synchronization conflict. And this is different from conventional cache coherence. In conventional cache coherence, you simply mark the conflicted data as being invalid, and then you forget about it. Here, you have to go back and say, oh, this is a synchronization conflict. I need to throw out any changes I've made and start over again. So this is a more expensive undertaking, but you can see that it uses the same machinery that conventional cache coherence uses. So we've added a little bit of control logic and a few extra bits to each cache line. So it's not a big change. How do we commit a transaction? So at the time when I decide I want to commit, if there were no cache conflicts, if there were no invalidations, then we say, okay, I made it all the way to the end of my transaction with no conflicts. I'm going to go to my cache and I'm going to bless it and clear all the transactional bits. So I just turn off the transactional bits, and now it appears as if I woke up, executed all of these statements at once with no interleaving, and now I can say, pretend that it happened atomically. I find all the transactional cache entries. If they used to be read-only, then I mark them as being valid, meaning that this is a good copy of the data. If it was modified, then I mark it as being dirty. This is an intermediate state that says that the data in my cache does not agree with memory, and I need to write it back at some point, but maybe not now. So the synchronization here is kind of passive in the sense that we rely on the hardware coherence mechanism to inform us of synchronization conflicts. How we react to synchronization conflicts is slightly different. And how we manage to cache is slightly different, but not extremely different. So that's almost everything. When I talk about how to program these things, say on Intel machines, we'll see that there are a few complications that show up. You know, the general theme is here is a beautiful abstraction that we can use. Well, actually, we can't implement that abstraction. We have something that's a little bit more complicated. Well, in fact, I didn't tell you the entire truth. It's even more complicated than that. So we're going to see a number of these things here. So what was it? 10 minutes, okay. So what I'll talk about next is how to take this raw hardware and start writing programs with it. So the reason, as I mentioned before, the reason that I'm telling you about the hardware is because in order to understand the software behavior, you need to understand how it's implemented. And again, this is something that you don't see in more mature areas. So we don't worry that our compilers are going to fail. Why did our compiler fail? Well, because the parsing algorithm has bugs. You know, we don't have to worry about that, but we do have to worry about similar things when we talk about transactional memory. So there are a number of existing hardware transactional memory systems. So IBM has at least 3, and they're not exactly the same system. The Blue Gene Q was intended to use transactional memory to do automatic parallelization of scientific computing. So what their application is they have these big programs where they have loops. And most of the time, the loop bodies don't interfere with each other, so you can execute them in parallel. But sometimes they do interfere with each other. So particularly if you have multiple levels of indexing, it's very hard to tell whether there is a synchronization conflict or not. And you may say, I'm really sure that there is no synchronization conflict, but I can't prove it. I'm really sure that there's no synchronization conflict except one every 10 million times there is. Then what do you do? If you're cautious, then you put a lock and everything is very slow. But the nice thing about speculative transactions is if most of the time there is no synchronization conflict, then the hardware transactional memory will let the loop bodies execute in perfect parallelism. And the one time in a million where there is a synchronization conflict, it will detect that, it will roll back the transaction and start it up again. And you'll still get the right answer, but it will be somewhat slower. So speculation is a very powerful technique in cases where synchronization conflicts are sufficiently rare. If every single loop body interferes with every other loop body, then it's not a good idea to use speculation. You should just execute them in one-at-a-time order because you're going to end up doing that anyway. So IBM Blue Gene Q is a little bit different from what I described because they do their speculation in the L2 cache, which is much bigger than the L1 cache that I described here. Now, if you don't know what this means, don't worry about it because this is all intended for people who care about this. Now, most of the actual transactional programming you're likely to do is probably going to be on an Intel processor. So currently, every Intel laptop you buy has support for hardware transactions baked into it. Sometimes they disable it to save power for small machines, but on servers or graphics machines, the transactions are turned on. And they call this a TSX extensions. So it's an extension to the i86 architecture. So this is what a program looks like. What a transactional program looks like if you use the hardware transactions. Now I'm writing this in C for good reason because C is basically the most natural language to use because everything is provided through these magical libraries that Intel will give you. Hardware transactional memory doesn't play very well with things like garbage collection because it can introduce all kinds of synchronization conflicts. Making this work is a research issue. And you could, of course, do this in C++, but C is the most natural way to do this. So the interface is a little bit odd. So the underscore xbegin starts a speculative transaction. So again, a speculative transaction is one where you make changes, you make tentative changes, and if you commit, then they all become visible at once. And if you abort, it gets rolled back. Now, xbegin is a little like fork or vfork in Unix in that it returns a return code that tells you where you are. And this is, this is a little bit strange. So you start a speculative transaction, and if you see this code, then you are executing your transaction. So I make this system call. If it comes back with this particular constant, then I know that I've just started a speculative transaction and I'm inside the transaction. If I get any other code, then I know that I tried to execute my transaction, but it aborted. It failed for some reason. For what reason? Well, you can look at the code and that gives you some information about what happened. If you get back an abort code, then you have a choice. You can say, well, I tried to execute this as a speculative transaction. What happened? So I can look at the code and say, well, what happened was I had a synchronization conflict with another transaction. So in that case, I should just try again. Maybe I should back off and and wait for a bit. But if I try again, then I'm likely to succeed. Or you can say, well, my transaction aborted because I executed an illegal instruction. Then it's probably not a good idea to try again because the same thing will probably happen. So then I should do something else. So all of these programs have this structure where I can either execute the speculative code, I can react to a failure code and either retry or do something completely different. So there are lots of abort codes. So here, for example, if you're inside a transaction, you can explicitly abort it. I could be executing my transaction, I could look at it and say, I don't like this. Maybe my user just hit a big red panic button, and I'm going to throw everything away in panic. So when I return, I say, I explicitly aborted this, and you can also pass a second code saying why you chose to abort it. This is maybe useful for debugging. Debugging transactional programs, as you can imagine, is difficult. It could be that a synchronization conflict happened. So this says, I'm going to take my status and I'm going to check the conflict bit. So this is a bit masking operation. And I could say, well, if there was a conflict with another transaction, then I should probably try again. Because unless there's a lot of contention, the next time I try, this will succeed. Or what could happen is that I filled up my cache. Remember when I showed you that picture of the dirty data? So a transaction reads in a piece of data, puts it in its cache, modifies it. I told you you can't write that back to memory because it's speculative. It isn't real yet. What happens if you fill up your entire cache with this dirty data and you can't write it back? Well, then your transaction will abort because it's too big. So this is our first crack in our abstraction because you could write a program that is perfectly okay, but it will never commit because it fills up your cache. And the abort code will tell you, sorry, you filled up your cache. and there's really nothing you can do there. You might not know how big your cache is. You might not control your compiler. Your compiler might be reading unnecessary things. But if it comes back and says that you had a capacity abort, then that says, well, you're probably better off doing something else, that a transaction is not going to succeed here. Yeah. This is done on a cache line basis. So this is, again, you might say, well, this is horrible that I need to worry about these things, but you do need to worry about these things. And this is because these are immature constructs. You know, if I give this talk 10 years from now, this will be much smoother, and I'll tell jokes about the old days when we had to worry about cache alignment and things like that, and how horrible it was. But you know, today this is what we have to deal with, and this is why, in fact, I tell you about the hardware so you understand why this is an issue. You know, again, in 10 years, perhaps I don't need to talk about the hardware the same way I don't need to talk about disks for virtual memory. And there are lots of other abort codes. And sometimes you can have more than one abort code, which is why, you know, we're doing all of this masking and so on. So this is, yeah. Yes, so the question had to do with the analogy between the xbegin and a fork in Unix or Linux. And the questioner correctly pointed out that the way this works is you call xbegin, and if the transaction should fail, then the underlying hardware and software resets the program counter to the place where you returned from the xbegin call, but changes the return code on the stack to indicate to the abort code. So it is this is a programming pattern that is familiar with people who work on Linux kernels. Is probably not familiar to people who write Java programs or higher level languages. But the hardware guarantees that the second time around, it looks as if you just called this and it returned immediately with an abort code. And then all of the other code shown here is just all the sequence of tests. Say, did this, you know, what happened? Did this happen? Did that happen? Did something else happen? Did that answer your question? So you can see that there's a distance between this style of programming and the elegant atomic block that I showed you at the beginning. You know, so yes. Oh, so the question is, by analogy with set jump and long jump, which are also system calls that do mysterious things with program counters, is it expensive to do xbegin? I think it's not very expensive in the sense that a null transaction is only a few cycles. This may change from one version, from one Intel processor to another. So it's currently I believe it's reasonably efficient to do an empty transaction. Yes. In a perfect world, that would be true, but the problem is L1 caches are not always fully associative. So if you have a set associative cache, then you can break things by just filling up one set. So if your set has 4 elements and you are very unlucky and 5 of your variables map onto that set, you're out of luck. And this is bad because you typically have very little control over this. So if you're writing a C program, you can pad everything and line it up, and you can have macros that know how big your cache line is and so on. But in Java program, good luck. So again, these are things that in principle could be deadly. In practice, this doesn't really happen so much. You can turn off optimization levels and everything, the layout changes. So the worst case is bad, but in practice is not so bad. But again, in order to program this, you need to understand what the worst case is, and you need to understand that the abstractions are broken. But it's still, I think you're still better off than using locks. Yes. Yes, what it does is it goes through the. Yes. So if you detect if one cache line is invalidated, then the cache handler will notify the processor and say, okay, everything that's transactional, mark it as invalid, reset the program counter to xbegin, and provide a code. Yes. So inside a hardware transaction, you want to be careful to not make it too big or run too long. And I'll say a little bit more about that. From an abstraction point of view, this is terrible. From a practical point of view, well, life is difficult.